Wow. 230. Wow.
Is it working?
Yeah. I took everything.
Is it bouncing? La 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 la. La la. La la la. Da.
Yeah.
Has it got me? All right. It's my default. Ah. Silas is on the road.
Is he really?
That's what he said. Okay, so let's continue on here. So we're still talking about logs and exponentials. So I've covered pretty much all of the problem types in section 4.5 with you guys, but there is one remaining sort of thing to do in terms of those examples, and I'll do it right now. Find f inverse of y given f of x is equal to e to the 2x plus 13. All right, so we've talked about finding the formula for an inverse function before, right? But we haven't done it recently with our newfound algebra, right? So let's go through that. How do we find the formula for the inverse function, given that the function is defined like in terms of an exponential? So it's the same thing we did before. We start by writing y equals to the formula. And what do we do after that? Next move, we solve for x. So how do you solve for x here? What do you do? Get rid of the e. How do we get rid of the e? Yeah, take the ln of both sides. Natural log of y is equal to the natural log of e to the 2x plus 13, but that is 2x plus 13. Right, what you just said, 1/2 of the natural log of y minus 13. Yeah, indeed, boom. This is exactly inverse of y. There it is. You want to do another? Sure, why not? Example. F of x equal to the log base 8 of 7 minus x. Suppose we want to find the inverse function here. Find the Again, find f inverse of y. So step number 1, we write y equals to the formula. E to the 8, your heart's in the right place. Admittedly, we don't have really a good way of verbalizing this. I usually say it's like exponentiate both sides base 8 or something like that. But raise both sides to the 8. That's not right either. 8 to the y. A smart instructor will just hide the fact they don't have a word for this and just say, well, do this. So of course, the right-hand side, the 8 and the log base 8, they cancel, right? So this is 7 minus x. And over here, so what we got is x equal to 7 minus 8 to the power y. And so thus f inverse of y is equal to, 7 minus 8 to the y. So if you understood how to calculate the formula, like to find f inverse of y previously, there's nothing really too surprising here. It's just using our new, exponentials and logs. Okay, so great. So next up, I'm going to talk to you a little bit about hyperbolic trig functions. So just to start out with, I always tell people about this. If we have a function, f of x, right, then one thing we can do is write this sneaky formula. So what do you think? Does that make sense or does it not make sense? What do I need to know to make sense of that formula? Like one thing is 1/2 plus 1/2 is 1. I think we can all agree with that, right? And I've also added 0, right? Because I've added and subtracted f of minus x over 2, right? So this is an identity, but we do need something else, right? We need that both x and minus x are in the domain of f, right? This is, I'm assuming, x and minus x are in the domain of the function. If I have that property, then I have this identity. So certainly if the domain of the function is all reals, we can do this, right? And the neat thing about doing this is if you study this piece right here, you can see that that's actually an even function. Right? Just think about what happens if I replace x with minus x. What happens to this formula? If I put in minus x in the place of x, I get f of minus x plus f of minus minus x. But that's the same two terms, just in opposite order, right? So like if you change x to minus x, you can see that this part of the formula is again what it is. So the first two terms give an even function. In contrast, what happens over here if you replace x with minus x? You're going to guess odd, yeah. So we get f of minus x here, and we get f of x over here. If you factor out the minus, you've got what you started again. So in short, this is an odd function. So what I'm just showing you is this little bit of algebra shows you that any function with a domain which is symmetric about the origin can be decomposed into the sum of an even function and an odd function. And in fact, uniquely so, because those formulas show you the unique decomposition. Now, what happens when we apply this to the exponential? We have 1/2 e to the x plus e to the minus x plus 1/2 e to the x minus e to the minus x. So this gives me two functions, which are even and odd, and we have names for these. This guy is called cosh of x. This guy over here is called sinh. This is the hyperbolic cosine. This is the hyperbolic sine. First thing I would observe is, like, what's cosh of 0? What's sinh of 0? You guys work those out for me and tell me. Fill in the blanks for me. So what is e to the 0? No, e to the 0 is 1. Indeed. What's that?
Checked out today.
Have you literally checked out from your dorm already?
Yeah.
Okay. That's good. I never checked out from my dorm.
Really?
Yep. I never was in a dorm.
Good one.
I stayed with I stayed at NC State, and well, the first 2 years I commuted to a community college that was like 30 miles away, 30 minutes away, and then I also commuted to Appalachian State University, which is in Boone, North Carolina. Kind of lived halfway between those. And in fact, at one point I was taking classes at both. But then I transferred to NC State in like '98. Was there for like 3 years, but I think.
So by then you didn't have to live in
No, exactly. So I lived with a nice little lady named Miss Matthews. It was like about mile off campus, something like that. I ride my bike, make it to class in like 10 minutes. It's pretty good. I didn't hit too many people. People get really mad if you hit them on a bike. Yeah, there's like some choke points. There's this thing called the Brickyard, and like to get on the Brickyard, you have to go through this like little post area where they've got a couple of keep people from riding their whatever ATVs down in there. Whatever, I mean, what I don't know whether they're gonna ride, but cars, I guess. And so going through those posted areas, you'd end up like getting pinched with foot traffic, and if you're not careful, you run into people. I think I only did once. He was really mad though. Anyway, so 1/2 of 1 plus 1 is 1. Cosh of 0 is 1. What's sinh of 0? 0. Very good. So I know some of you have seen trigonometry in high school, right? Admit it. Yeah. So you remember, what is cosine of 0 equal to? What's sine of 0 equal to? Remember, cosine of 0 looks like this. I mean, cosine looks like that. Sine looks like this. So like sine of 0 was 0. Cosine of 0 is 1.
So I was right.
You're right, yes. So this is part of the reason that hyperbolic sine and cosine are called hyperbolic sine and hyperbolic cosine, because they are very analogous to sine and cosine, right? I mean, that alone does not prove it. It doesn't explain the name. I'll keep explaining as we go on here. The next thing I might ask is like, what about graphs? What is the graph? So in short, this is what they look like. So cosine of 0 is 1. I mean, cosh of 0 is 1. And it does like this, basically. So let me put it this way. If we think about cosh of x, it is approximately e to the x over 2 for x much, much greater than 0, right? Or maybe I can say, let me just say it more like this, for x going to infinity, right? Whereas cosh of x is approximately e to the minus x over 2 for x going to minus infinity, right? So e to the x over 2, it looks like this is y equals e to the x over 2, okay? This is y equals e to the minus x over 2. So if you take those two things and you add them together, they go through, like this one goes through a half, that one goes through a half. When you add them together, you get 1 here, and then they like both blow up, going either direction. So it's it roughly resembles like y equals x squared plus 1, but that doesn't do it justice because it's got exponential growth on both sides. It's going like super steep, right? That's what cosh looks like. What's the range of cosh x, by the way? It's 1 to infinity. All right. Sinh y equals sinh x. It's approximately e to the x over 2 for x going to infinity. And it's minus e to the minus x over 2 for x going to minus infinity. And so what that does is something like this. So what's the range of sinh? Well, the range of sinh is all real numbers, right? The range of cosh is just 1 to infinity. All right. Oh, did you already pan over? Okay. So there's more. Definition: hyperbolic tangent is equal to what? Now, for those of you who've had trigonometry before, you remember how we defined tangent? Tangent theta was what? What was it? It was sine theta divided by cosine theta. You may or may not remember that. If you don't, it's fine. It's not part of this course, right? So what do you think hyperbolic tangent is? Sinh over cosh. You are correct. Right. Now, this you could write, what's a formula for it? Tangent of x is equal to 1/2 e to the x plus e to the minus x, well, minus e to the minus x, right? Divided by 1/2 e to the x plus e to the minus x, because that's what cosh and sinh are, right? So the half cancels, and I would point out to you a couple of useful formulas to know about tang. One is that it's e to the x minus e to the minus x over e to the x plus e to the minus x. That's mildly useful. But one of the things we could do is just take that and multiply by e to the x over e to the x. What happens if you multiply this by e to the x over e to the x? What do you get? We get e to the 2x, right, minus 1 over e to the 2x plus 1. Why would we do that? Yes. And then also, if we take this and we multiply by e to the minus x over e to the minus x, what do we get? I will answer your question eventually. What's the difference? This one gives us what? 1. We get like 1 minus e to the minus 2x over 1 plus e to the minus 2x. These formulas are useful in thinking about what the graph of the hyperbolic tangent looks like for large or very large positive or very large negative values of x, right? Because, like, what are the key ideas about exponentials? If you'll allow me this notation, limit as x goes to infinity of e to the minus x is 0, and the limit as x goes to minus infinity of e to the x is equal to 0. But I can just as well put a 2 here or put a 2 here, you know. So what happens, like the yellow expression, if you think about x going to minus infinity, what's that go to? Zero minus 1 over 0 plus 1 This is as x goes to minus infinity. In other words, minus 1. How about this one? What's this go to as x goes to infinity? We get 1 minus 0 over 1 plus 0. We get 1. So that shows you that the hyperbolic tangent has horizontal asymptotes of minus 1 and 1, actually, as we go to plus or minus infinity. So with this in hand, I can graph the hyperbolic tangent. I'm going to erase these limits. You guys got it? The limit part down here? No? Give you a second. Is what? I am expanding on a homework problem which is given in Chapter 4. And there's homework questions about this in your mission 5, which I will project, hopefully, before the end of this class. Keep track. Yeah, we're fine. So, so in short, guys, the graph of hyperbolic tangent looks something like this. So what's the range of the hyperbolic tangent? Negative 1 to 1, neither of them included, right? So, fun facts. Cosine of theta, well, cosine of minus theta is cosine of theta. Sine of minus theta is minus sine of theta. In other words, cosine is an even function, sine is an odd function. Same is true for hyperbolic cosine. And hyperbolic sine. There are some differences, though. There are some pretty significant differences, and one of those is the well-known Pythagorean identity for cosine and sine, right? Cosine squared theta plus sine squared theta is what? It's 1, right? And by the way, notation is what? This cosine squared theta, what's that mean? This is our silly shorthand for cosine of theta squared. Which, by the way, is kind of an unfortunate notation because we also use like cosine to the minus 1, but it doesn't mean the reciprocal. It means the inverse function to cosine. So there's a hypocrisy in the use of this notation that is commonplace. You got to be aware of that. Yeah.
This must be a negative in front of the cos of x.
Nope. Cosh is even. It eats minuses. In other words, it does. If this is x, this is minus x, same point. Right? Whereas with the sinh, if you go to x here and x there, it's like up here, but it's down there. It's odd. Now, so this is, I sometimes call this the Pythagorean identity for cosine and sine. What does this mean? Remember the unit circle? The unit circle is a set of all points which are equidistant from the origin, right? So if I was to take the unit circle, I could say, if I pick this point here, right, and if that's at angle, let's say t for the sake of being different, then that would be cosine t, sine of t. Many of you have been taught in a trigonometry course in high school perhaps, that you can use this unit circle with particular values labeled to calculate values of sine and cosine, right, as like kind of a memory tool, a way of remembering a hodgepodge of values for sine and cosine in this way, right? But another way to take away from this is that cosine and sine do what's called parametrize the circle. So this is a parametrization of the circle. Parametrize circle. What's the equation of the circle? The equation of the circle is x squared plus, I mean, this is something we covered, right? X squared plus y squared equals to 1. So if you take the parametric formulas for x and y, cosine t and sine t respective, you plug them in there, it works, right? You cosine squared plus sine squared is 1, right? So cosine and sine parametrize the circle. And that's why sometimes you might hear people call sine and cosine circular functions, right? So the interesting thing about hyperbolic sine and hyperbolic cosine is they satisfy a similar identity. In fact, they satisfy something like this: cos squared x minus sinh squared x equals to 1. So it's very similar and yet different, right? And if we had talked about hyperbolas in this class, which is the next natural thing to do, because it also involves completing the squares, and there's a larger discussion of something called conic sections, because the circle and these hyperbolas, they're both things that you can get from taking a cone in 3 dimensions and like taking a planar slice of it. May or may not have seen that in high school. It's all good. But the hyperbola looks like this. I mean, this is one kind. You can also look at ones that open upwards, but the one that opens sideways like this is x squared minus y squared equals to 1. And if you want, you can parametrize a point on this hyperbola by cos t, sinh t. So hyperbolic sine and cosine are also so called hyperbolic sine and cosine because you can use them to parametrize hyperbolas. And they're also just natural things that appear in what's called the study of hyperbolic geometry. So if you study Einstein's special relativity, you can look at space and time. So people draw these space-time diagrams. And in a space-time diagram, you make like CT or time go up and you make space go right. And in those pictures, the hyperbolas have a special significance. They different inertial observers can agree on points in hyperbolas. But anyway, I shouldn't get into all that. But the point is, like cos and sinh appear in like special relativity in a natural way. People associate the hyperbolic tangent to something called the rapidity. So if you have an object which is moving, you can talk about its rapidity. It's the hyperbolic tangent of its velocity divided by the speed of light. And one of the interesting things you learn is that if you have an object and it's moving and another object is propelled from that moving object, then the way the velocities add is not just to add velocities, you actually add the rapidities of those objects. So if you were to study special relativity, you'd see hyperbolic sine and cosine all over the place. In fact, that's the first place I saw it, because I was deprived of hyperbolic sine and cosine from my major coursework. Like, it didn't pretty much appear in calculus or pre-calculus for me, which is unfortunate because they're actually important functions that give you a lot more insight into other things. Because they're another side of the story of sine and cosine, really. They'll give you additional insight into sine and cosine. Now I will momentarily really misbehave. I'm going to take my misbehaving to another level at the moment. But in fact, you can write cosine itself in terms of an exponential. But it comes at the cost of looking at what's called an imaginary exponential. So these are the formulas for sine and cosine in terms of imaginary exponentials. You can derive trigonometric identities with these in algebra. All right? Let me show you such an example. Let's try cosine squared theta plus sine squared theta. We all know that that's 1, right? Actually, let's do something more interesting. That one's 2. You already know that. That's not impressive. What is twice sine theta cosine theta equal to? Anybody remember? Well, if you're soon taking a course in physics, you need to learn this one because we use it. Let's find out. We don't need to look it up. We can derive it if you know these formulas. So this is 2 times 1/2 e to the I theta minus e to the minus I theta, and then 1/2i e to the I theta minus e to the minus I theta. And let's just bring the numbers out front. So we've got 1/2i. And then just FOIL, like just multiply like usual. Like what's e to the I theta times e to the I theta? Well, that's e to the 2I theta. What's e to the I theta times e to the minus I theta? Should be e to the 0, right? Because we plus I theta minus I theta, so we get e to the 0, which is 1, so plus 1. And then what about e to the minus I theta times e to the I theta? Well, that's also 1, but you got a minus, so we get minus 1. And then e to the minus I theta times e to the minus I theta, minus minus gives me plus, I get plus. Wait a minute. Why do I have 2 minuses? Dude. One of these is not a minus. This one should be a plus right here, right? Fortunately, it hasn't hurt us yet because I ignored the fact that I had plus minus there. So haha, phew. It made an even number of mistakes. It worked out. So minus times plus, I should have a minus e to the minus 2I theta. So the 1 and the minus 1 cancel. And what you've got is 1/2i e to the 2I theta minus e to the minus 2I theta. What's that? You don't even thought this is math? Oh, man. Hurt me with that. All right, now, so what's this here? Look at that. Look at this. What is this expression in terms of sine? Sine of what? Sine of 2 theta. Look, we just derived the identity that 2 sine cosine is equal to sine 2 theta. If you know the identities for sine and cosine I'm showing you, you can use the algebra of exponentials to derive pretty much every trigonometric identity that you can come across. This is not what we're going to teach you next semester if you take trigonometry. This is a forbidden jutsu, if you will, a secret knowledge which is hidden from the masses because we fear teaching anyone complex variables except for those who take complex variables. You can guess my opinion of that. But anyway. All right, so, but again, this further shows you the analogy between cosh and sinh is even deeper, right? Because you can put it together. What do you got? Cosine Well, if you take cosh of I theta, what do you got? Plug in I theta into the formula for hyperbolic cosine, which I've erased. It's exactly cosine. And if we look at sinh of I theta, it's exactly minus I sine theta, or actually just minus sine theta, I think. If I remember right. Wait a minute, no, I need an I, minus I sine theta. So, in fact, cosh and sinh and sine or cosine, from a complex perspective, are almost essentially the same functions. So you can't disconnect yourself from the study of trigonometry and the study of hyperbolic trigonometry. They're like necessarily, and they're linked. Anyway. Now, all right, so that obviously is bonus material, right? I don't even have a homework question about that. I'm just totally misbehaving. I hope you can forgive me. For what it's worth, I had a student who actually discovered a way of thinking of the derivation of the trigonometric identity and the hyperbolic trigonometric identity as part of the same story. He has a derivation which derives both of these at once. And in fact, there's a accountably infinite tower of these identities for higher trig functions. Like, you could look at sort of the in some sense, this is based on two-ness. You could look at something based on three-ness, and you can define what I call the Larry, Moe, Curly functions, and then you get the Three Stooges identity, as I call it, which, if I recall correctly, is Larry cubed plus Moe cubed plus Curly cubed minus 3 times Larry, Moe, Curly equals to 0. But I could be wrong about that. It's been a while since I looked at the Three Stooges identity. But anyway. I'm not joking. F of x. Oh yeah, that kid's smarter than me for sure. F of x is. Let's say f of x is sinh of x. What question am I going to ask you? What's x? I'm going to ask you to find the formula for the inverse function. Find f inverse of y. So what do? We got y is equal to 1/2 e to the x minus e to the minus x. Right? And now I need to do what? Solve for x. Whew. Now that starts to sting a little, doesn't it? So this is e to the x minus 2y minus e to the minus x equals to 0. Now there's a problem that's kind of sort of like this in section 4.5, but we didn't cover it in here. I covered it in the other section. For whatever reason, we just didn't hit it. But there's one like this. I think it's 43. 43 is kind of the same pattern as this. This one's tricky. Like, what you got to do is you got to multiply by e to the x to make it into a quadratic. So this is e to the x squared minus 2 y e to the x minus 1 equal to 0. Now it's quadratic in e to the x. So we can use that quadratic trick, right? And let's see here. So I'll complete the square. We have e to the x minus y, quantity squared, plus y squared minus 1 equal to 0. Excuse me, I should subtract y squared. In other words, e to the x minus y, quantity squared, equals to 1 plus y squared. And then we take the square root. Yeah? So e to the x minus y is equal to plus or minus the square root of 1 plus y squared. So e to the x is equal to y plus or minus the square root of 1 plus y squared. Now, if you think about this, only one of those has a solution, right? Because if 1 plus y squared is larger than y, if we square root it, right? Think about that. So if we subtract, we're going to not have a number less than 0 if there's no solution. So we can just focus on the plus. Right, so just the plus is all that matters. And so then take the natural log of both sides. We've got x is equal to the natural log of y plus the square root of 1 plus y squared. There you go. F inverse of y is the natural log of y plus the square root of 1 plus y squared. Or you could write this. Inverse hyperbolic sine of x is in fact the natural log of x plus the square root of 1 plus x squared. So that's a really bizarre result when you first see it. What's that? Oh, so I won't talk about your homework. So you don't want me to talk about the homework? Is that what I'm hearing? What's that? I can. Because it'd probably be good for me to point out that I've worked a couple of your homework problems today. I know, right? Which ones? Get this thing rolling. So I haven't posted the homework yet, right? But I have written it, and so it should be posted right shortly after class. I'll post it.
When is it going to be due?
It's due online, so that's a good question. When's it going to be due?
Shoot for after Thanksgiving break.
You say during Thanksgiving break? Come on, computer.
How will our exam go?
Well, I don't know about that. I guess I could ask you the question. How did your exam go?
No, like how will I mean like the one at home?
How's the one at home go?
Yeah.
Well, that one's going to be open book, and so like open book, you can use like Wolfram Alpha, stuff like that. It's fine, but it will be at the final exam time by Zoom, I think. I should send an announcement about that, but
By Zoom, like what do you mean how?
I mean, you have to Zoom. Why do you have to Zoom? I'm making it open book. I don't know. I'll think about these things.
That really does make any sense.
What about the recent tests we took? When will we get those scores?
When will I have the recent test you took graded?
Yes.
Oh, that's anybody's guess. Let's see here.
That's what?
That's anybody's guess. I mean, I don't know. See, the trouble is if I grade that before you guys do if I grade that before you do final exam part 2, then all of a sudden you're just not going to do final exam part 2. What's that?
At least it makes me
You're like, yes, that's why I want.
that right, then that makes me feel like I know what I'm doing.
Oh. That was a bad angle. Oh, goodness gracious. What have I done? I don't either. Ugh. Come on. Stupid. Oh, come on. Are you kidding me?
Speaking of checking out from my dorm, I forgot to put it in.
Come on. All right, finally. Can we, you got it over there? You good? So there are 25 points. That means there are now, I think, 55 bonus points available from homework. So I have two problems. They're just fit the graph. Those are kind of self-explanatory. Simplify log of blah, expand, contract, solve equations like we did in class. This one we didn't do, but you'll figure it out. Problem 80 and problem 81 are awful like the ones I did to start it today, as is 82. Problem 83, you're proving the fun facts, one of which I mean, there's really not much. These are easy to prove. You can, but do it. And then notice 84, I said find f inverse of y for sinh. We just did that. You should be glad I did that for you. Yes? Because that was not easy. It turns out that the similar calculation for hyperbolic tangent is easier. And there you go. That's your homework. So enjoy it. See you guys next semester, maybe? Somewhere, perhaps?
Bye.
Bye. Come back to the math major.
Oh, I don't know about that.
At least start with a minor.
That's a strange
Ah.
concept.